classification using neural networks, where we just built is, I think, a couple of layers of dense neural network, which was taking x, the feature vectors x as input, and I think it was classifying. It was giving you y hat, the class y hat denotes the class of x. So this neural network was trained to take x and classify it into the classes. So we went over the exact equations that define the outputs of each layer and the outputs of the neural network when you give it the input x. And then we trained this neural network by defining a cost function, which I will go over briefly. And then we showed that if we use gradient descent, how can we set up the back propagation to calculate the gradients. Since in gradient we are using gradient descent to solve for weights and biases. So let me just briefly go over this, because it's important that you have this fresh in your mind before I start with the next topic. After doing this, we went over a different architecture of neural network that was convolutional neural network. Everything was the same, only the layers were convolution. So I went over in detail on the motivation of using convolutional neural networks. We had a slide. I had given you the link to that page that I used to introduce neural networks. So the main motivation neural networks, convolutional neural networks, GT, that we wanted to reduce the number of weight parameters from layer to layer. Second motivation was, and very important motivation was, that these were suitable for image classification tasks, because as we went over in detail, the convolutions are invariant to shifts of the image, translation invariance. So we covered that. So let me just start with this particular multi-class classification handout. So this is X is the input, Z1 was the output, H1 was the output of the first hidden layer after the nonlinearity sigmoid, Z2 is the output of the second hidden layer, which takes H1, the output of the first hidden layer, as input. And the y hat is the final output, final layer, which takes Z2 and applies this softmax function. Again, to remind you, y hat is the probabilities, and the length of y hat was k. The k is the number of classes. So softmax operation is basically just taking the last layer, Z2, and just like renormalizing it so that it sums to 1. And we use these exponentials to just make it numerically stable. We went over it. And then like what I did was I wanted these y hats to be like, give me higher value at the position of the true class. So if it is a length 3 vector, there are 3 classes. If it is class 2, I wanted the second category, second entry of y hat to be bigger than the first and the third entry. All of these entries sum to 1, remember that. So that is telling us that second entry is more probable than the first and the third entry. Based on this, we decide the class. So in this case, it would be the second class. So we set up the conventional cross entropy loss function, which was the true labels y case and the log of the output layer summed over the k classes. So remember that y over here is a 1 hot vector, which has an entry 1 at a location which corresponds to the class number. So our main method was that I wanted to minimize this cost function with respect to the parameters theta. The parameters over here are the weights and biases of the neural network, right? So that was our main scheme. And the rest of the handout was how should we calculate the gradients of this cost function with respect to the weights and the biases of the neural network. Then we defined all these gradient rules, which I won't go over again. And we calculated the gradient, for example, of this cost function f uh, with respect to the weights w. So where do w come over here? W's are inside this y hat k, and y hat k is related to w1 and w2 through these set of equations. All right, so we went over these series of steps and we calculated that the derivative of, we used chain rule, basically back propagation chain rule, that the derivative of f, the cost function with respect to w2, is just h1 y hat minus y transpose. Similarly, the derivative of this cost function with respect to biases, we computed this y hat minus y hat is the output of the neural network, y is the true label one hot vector. And then we went over and computed the derivative with respect to first layer. These are the derivative with respect to second layer weights and biases. And then we went over and computed this for the second layer, first layer. That was the partial derivative of f with respect to w1. This should be partial f or partial w1. So you can fix this mistake. I'll update it. And then this was partial. Main takeaway message over here was that, let's see, so in general, for an L layer network, if we generalize all of this, we'll see that for an L layer network, a two-layer clear, you had this true label subtracted from the output of the neural network transposed multiplied by W2 multiplied by this diagonal matrix, which is just the derivative of the softmax or derivative of the sigmoids, and then this identity. So if you generalize this formula, you will have for an L layer network y hat minus y, just like over here. And then the Lth layer, derivative of its sigmoid layer or nonlinearity, whatever it is. Then the layer next to it, WL minus 1. Just before it, sorry, the layer just before it, WL minus 1, and the derivative of its nonlinearity, and you continue till the layer which is just ahead of the layer with respect to which you are computing these derivatives. So the layer just ahead of L is L plus 1. Okay, so this is the general rule if you want to compute these derivatives for an arbitrary L layer network. So these are the gradient rules. You can use gradient descent. I could write gradient descent. I think it's written over here. We don't have to write it here. So this is the update. You will update the weight of an Lth layer by taking the by updating the previous iterate of WL with the gradient. This is the gradient which we computed up here, and alpha is the step size. So we will implement this as I told you in a very detailed lecture on this already. We'll implement how to compute these weights and biases that best fit the training data using gradient descent. So all of these equations are written over here. All you have to do is just go and code this up. So I have the code written down. I won't show you that. You'll have to code it up yourself. The code is over here. Everything is given over here. I think in the current homework we gave you a couple of questions related to this, but if we haven't, we will give it in the next homework. So the questions basically will be that you will be given these very simple, probably 2 or 3 dimensional X vectors as the training data. There will be many X's and the corresponding labels Y's. And what we will ask you to do is just build a couple of layer neural network yourself using these equations, and then will give you the size of each layer. For example, here the number of neurons in second layer, in the first layer, at the output of the first layer are D1. The input dimension is D. So the outputs of the second layer are K, and the input of the second layer is D1. So you will give you the D1s, Ds, and Ks, and we'll ask you to train these weight parameters and bias parameters and show us, did you get, what's your classification accuracy? Do it using gradient descent, and all of the equations are given over here. So now one more thing that I mentioned earlier as well, that this is very simple. The weight parameters W1 is a dense matrix because it's a dense layer. There's no special structure in W1 and W2. And the outputs y hat are being used in this loss function. And this loss function was set up so that it encourages that y hat k are close to yk. That's all this loss function is doing. We also went over this in detail. Why are we selecting this loss function? It has some nice properties that gradients were not saturated, if you remember, which allows us to update the weight parameters in the gradient descent scheme. If the gradients are saturated, the parameters don't get updated. We don't learn anything. So if we do regression, we'll have a different cost function over here. We did regression cost functions in detail too. So probably we'll also ask you to set up, in a different example, set up this neural network for regression. In that case, you will use the output y, and you will have a continuous true output y given to you. Y hat will be the output which is given by the neural network, and you would want them to be close to each other. So we had gone over it. There was a loss function for that. We just minimize the difference between the true y and the output of the neural network using the L2 norm, which is sum of the squares. So basically this is what we did. So we have this y, which is in RD, for example, in R, let's call it R, J, and X was the input. X is in RD, and your neural network in this particular case will spit out y hat, which will also belong to RJ. You will set up the layers in a way that output is RJ, and the output layer will not be a softmax like this, because here I don't want the outputs to sum to 1, right? In classification, I did want outputs to sum to 1 because outputs are probabilities. In general regression problem, we don't want the outputs to sum to 1, right? So be careful of that. We'll give you the architecture of the neural network as well. Probably we'll tell you what are the nonlinearities that you want to use. Anyways, so in this case, for example, if you had just a one-layer neural network, so the output y hat will be a sigmoid, a weight, and the input x, right? That's how you would compute the output. Input xi will give you output y. Once you have y hat, what you do is you would just take the difference of true with the, and you minimize this, right? Minimize this over theta. Theta over here is W. I have ignored the biases and everything. I've just given you an example. You have a one-layer neural network which doesn't have biases, just weight parameters, which takes input xi, applies a weight function, and gives you of nonlinearity the y hat i's. So we wanted to do this, and also remember that we just used one example over here. If you had more than one examples, you would just do the summation I is equal to 1 to n. Minimize it over w's. W's are inside this. So if you write this out, it's going to be sorry. If you write this out, it's going to be minimize again this sum yi minus sigma wxi. So you will just, this is your cost. I just replace y hat I will this its value so that you can exactly see that it's dependent on w. So now you can take the gradients. You can compute those gradients just as we did. We did this using chain rule and find out what are the gradients of. If I call this cost f, you will have to just compute delta wf. And then once you have it, all you have to do is this, just set up this gradient descent update, which is step length. T is denoting the iterate, so t minus 1 as iterate is t iterate is obtained by subtracting the gradient of f from the t minus 1 as iterate evaluated at w is equal to wt minus 1. So let's see if you have any questions. So in this handout, I am consistently using this convention. So if you use these conventions, you won't have trouble with these transpose. So the thing is that you will have to use one consistent convention. So if I fix this convention over here, then all your transposes will be in the right location. For example, why did I get this transpose over here? What was the reason? Because I defined partial f or partial z2 to be, in general, when I define this to be the case k. If you take the derivative of a vector with respect to another vector, the output of matrix will be of the size of x multiplied by the size of z. That would be the dimension of the output matrix. So for example, over here x is length n, z is length k, so the output matrix has dimension which is n by k. Right, so let's see which is k by n, which is the dimension of z divided by the dimension of, multiplied by the dimension of x. So I think we went over it. So in this case, अगर आप इसी rule को इस पे apply करें, on this case, you will see कि और यहाँ पर जो numerator में चीज़ है f, it's a scalar, इसका dimension 1 है, z2 का dimension जो भी है, that is given to you, z2 का dimension I guess it's k. तो उस हिसाब से इसका जो dimension आना चाहिए output का, it should be 1 by k. So ये 1 by k ही है, क्योंकि y hat minus y is a column vector of length k, उसका transpose देंगे तो वो row vector बन जाएगा, तो row vector का size is 1 by k. So don't worry about these transposes. If you stick to one particular convention, everything will be according to the sizes too. For example, यहाँ पर जो size मुझे चाहिए, it is important कि ये, अगर आप यहाँ पर size mess up करेंगे तो ये, अगर for example if I had written it h1 transpose y hat minus y, तो ये scalar बन जाता. This should be a matrix because you're taking the derivative of a scalar with respect to a matrix. So the gradient should be a matrix. According, ये आप इन conventions को ध्यान से देख लें. कुछ in some sources like books, convention different भी होती है, जिस तरह यहाँ पर partial f और partial x का जो size है, that is अगर x का size k by n है, तो इसका मैंने जो size रखा है वो n by k रखा है. This is how I defined it. आप इसको k by n का भी रख सकते थे डिफाइन, लेकिन फिर आपको बाकी सारे ग्रेडियंट्स भी उसी तरह से डिफाइन करने पड़ेंगे. ये मैंने कंसिस्टेंटली इस तरह किए हैं कि अगर मैं इसको इसमें डिफाइन करूँ तो बाकियों को भी मैंने उसी तरह सेट किया, सो दैट ओवरऑल हमारी चीजें एंड पे कंप्यूट होके सही है. तो let's see if we have any other questions. Forward propagation is that I give it an input and I propagate it through the layers of the neural network and compute what is the output. That's why I'm training the neural network, because I want to see the output of the neural network. So when you do forward propagation in testing, you get a test input, X test, and you want to suppose know its class. You propagate it through the network and you see what is the corresponding class. Back propagation, we have seen it. जो हम ग्रेडियंट्स के लिए यूज करते हैं वो ये है, हमने देखा है कि just compute the gradients, we need to take this output y hat minus y, जो आपका आउटपुट था y hat था, उसको ट्रू लेवल से सब्ट्रैक्ट करना है और उसको वेट्स के अंदर से दोबारा पीछे की तरफ मूव करना है. तो पीछे की तरफ मतलब ये है कि बिकॉज आई एम मल्टीप्लाइंग y hat minus y transpose from the left side of this matrix w hat, and you can think of it as कि ये जो लेयर है उसके आउटपुट पर y hat minus y hat wl लेयर जो है, और वो उसके ऊपर उल्टी साइड से पीछे की तरफ जा रही है और उसका इनपुट आपको यहाँ पर रिकवर हो जाएगा. तो इसको कहते हैं बैक प्रोपगेशन. सो दिस आउटपुट discrepancy between the true label and the estimated label that is being back propagated through the lth layer. Then you apply the derivative of the nonlinearity, then it is back propagated to the L minus 1 layer, and you keep back propagating it till just the layer जिसके पीछे आपका ये बैठा हुआ है W, just layer ahead of it. वहां तक पहुंच के you just update this WL. This is how it works. So this is why we derived these gradient formulas just to show you in this matrix form, okay, what really back propagation is, because I think it's very clear from this expression that what back propagation is. It is basically telling you that okay, you are multiplying the discrepancy, because training हो रहा है यहाँ पे, gradient should tell you कि कितना difference है between the true and the expect and the estimated जो आप estimate करें. अगर ये दोनों equal हैं तो आपका gradient 0 हो जाएगा और आप update होना आपका बंद हो जाएगा, which is exactly what we want. जब तक इन दोनों में error है, इन दोनों में difference है, so you will be always back propagating this error through your layers. Gradient इसी तरह compute हो रहा है. So it's easy for us to compute the gradients. So here we just have to back propagate our error through the neural network. So back propagation इसलिए यूज होती है, forward propagation तो हमें टेस्टिंग के लिए यूज करने को पड़ता. So that's it. This is what we did. इसके बाद हमने regularization भी मैंने motivate कर दिया था in the lectures. So that's it. So let's now move to, मैंने सही से motivation दिया आपको, उसमें सिर्फ motivation की बात थी जो हमने कर ली थी. Apart from the motivation, everything in the convolutional neural network is exactly, अगर gradients की बात करें तो वो back propagation वो इसी तरह ही है. उसमें W1 convolutional filter है, यहाँ पर तो ये dense एक matrix है, arbitrary matrix, लेकिन जब आप convolution करते हैं तो W1 becomes just एक मैंने आपको एग्जांपल दिया था, just becomes a filter. यानी अगर आपको फिल्टर वाली एग्जांपल याद हो तो उसके अंदर हमने क्या किया था, we had a filter, small filter which was going over the image, sliding across the image, और हर दफा फिल्टर का आउटपुट क्या होता था, जिन पिक्सेल्स के ऊपर फिल्टर था you would just multiply the filter weights with that particular set of pixel image and sum them up, and that would be your output. The same filter would slide over to the next set of pixels and you would do the same operation of summing the pixels, multiply the weights of the filter and sum them up to give you the output. So if you think of that, so that would mean that each row of this weight matrix W is the filter weights. पहली row for example क्या है, ये आपकी अगर X है, this is your image, आप उसको vectorize कर लें, और weights of the filter क्या होंगे, कहाँ पर नॉन जीरो होंगे, जहाँ पर आपने फिल्टर्स को वेट्स को मल्टीप्लाई करना था जिन पिक्सेल्स के साथ, उन कॉरेस्पॉन्डिंग लोकेशंस के ऊपर उस रो के अंदर W1 के अंदर वो फिल्टर वेट्स पड़े होंगे, And when you multiply this W1 with this X, तो वो basically वो weights multiply होंगे X की pixels के साथ, and you will sum them up, और वो यहाँ पे Z1 पे output पे आ जाएगा. So you can set this W1 X plus P1 equation just exactly as it is to depict convolution as well. So यही चीज रहेगी, यही same चीज रहेगी. You can then यही exact backward propagation algorithms होंगी, यही exact gradients होंगे to solve convolution to train the convolutional neural network. One important thing over there is वहाँ पर when you do these gradients, set up these gradients, तो आप you should basically tell your solver that okay, dude, this W2 is not a dense matrix, it's a convolution matrix, because if you treat it as a convolution matrix, you can save a lot of computation. In a dense matrix, every row is independent of the row above it. But in convolution, I mentioned every row for one filter, first row is the weights multiplied with some pixels, but the second row of this matrix would be same filter multiplied by different set of pixels. So your weights are the same. So you can, so the weights are the same as in the first row. The first row and second row share the weights, but their locations are different because they are multiplied with different pixels. So you can take advantage of this fact and speed up this multiplication. You can speed it up much more than compared to a simple dense matrix. So that is done automatically for you in TensorFlow or PyTorch. But if you have to implement it in NumPy and you're doing it for a big, huge image, you have to take care of this fact that this W2 is convolution, so that you can compute these gradients efficiently. Otherwise, your computer will just be taking a lot of time to compute these gradients. Anyway, so that's the implementation intensive aspect. In the homeworks, we won't be giving you too big of images. Probably they won't even be images अगर आप convolution को train कर रहे हैं. शायद या छोटी images होंगी जिनके लिए just part implementing W2 multiplication wouldn't matter that much. इसको computationally efficiently implement करना won't matter that much. Anyway, so let me see if you have any questions. So now I'll be going over in detail over these recurrent neural networks. That's another class of neural networks that is of interest for both computer vision and also for signal processing community as well, for natural language processing, text processing. So the main idea over here is that I want to build a neural network which is classifying a sequence. So sequence is, I'm going to denote it with, it's not one. Previously we had these feature vectors to be individuals, x1, x2, x3, and so on. These x's had no relationships with each other. And all I was concerned, for example, in classification was take this x1, classify it into a y1, and then the x2 was completely independent of x1, and I wanted to classify it in its correct class y2. x3 was to be classified in a class y3. Now what I am doing over here is I don't have this setup now. So इस setup के अंदर तो what we did was we just took a neural network, we give it xi at the input. So the neural network is represented by f, function f over here, and this would just give me yi. So this is what it is, y. So I trained this neural network dependent on the weight parameters theta. So I trained this neural network in a way that it maps xi to yi successfully. Right, so that was the setup. Now the setup is a little bit different. We don't have these x1, x2, x3 to be independent of each other. We have these as sequence. So there is some relationship between these. X1 depends x3. So this is what we have. These are x1, x2, x3. These are the, you can think of them as the readings of a time series. So that's x1, that's x2, x3, so on, x tau. I'm looking at these readings, and obviously now these have a sequence relationship. Xt minus 1 comes before xt, x3 comes before x4, so there is a sequence-wise relationship. I want to look at this sequence and I want to say, tell that the next one is xt plus 1. I want to tell that how to classify this sequence. What is the, can I, for example, in classification, what is the, there might be different categories I want to classify. This might be a stock values over last 1 year, over last 2 months. I want to classify how well, I want to classify it into good stock performance or bad stock performance. I could also ask a question that, okay, if I have an xt, what is the next predicted value xt plus 1? So in this case, it becomes a regression problem where you want to give x1, x2, x tau as an input, and I want to predict x tau plus 1. So this is like, I want to set up a neural network which, given all these history values, xt and all these histories, which this is your history, it predicts the next value, xt plus 1, which is a very relevant task in signal processing in machine learning. For example, in text, you want to probably look at a sentence and you want to predict what's the next word that's going to come out of his mouth, right? What's the next word he's going to write? So to predict the next word in a sentence, you need to take into account the previous words that were spoken or were written. But it is not clear in this context that, like, how many words in the history should I take into account? Whether I should look at last 3 words, last 4 words, last 5 words, last 10 words. So that really kind of, that problem means that I don't really know how many of these previous instances should I take into account. xt minus 1, xt minus 2, x3, x2, x1. How far should in the history I go to predict this next value, right? So that's one problem. I don't know the input size. Input size over here is just kind of, it's just flexible. It just keeps changing. So that's one problem. And then, like, another application is in language processing. You want to predict any signal you could take, for example, not even language processing, like you can think of stock prices as well. Any time series, I have the history of the values, these samples, and I want to predict what is the next sample. And I also probably want to predict in the future, farther into the future, that what are the future values. So this is forecasting. So all these interesting applications, sequence to sequence, they are called sequence to sequence models. Here I'm talking about sequence to a particular output, one fixed output. In a sequence to sequence model, you have all these x1s, x2s, xt's coming in. But at the output, what I have is, I'm not predicting one value. I'm predicting multiple values that change. Let me see. So here is the concept. So I have, let me draw it over here. I have x1 as an input, and I predict something y1. And then when I have a new input x2, I take a look at both of them, and now I update my estimate to be y2, because now I have an additional input coming in. And previously I just had x1, I wanted to predict y1. So is X1, you can think of it at a company current market value. You look at its stock performance, which is depicted in this feature vector X1. You look at it, you have just some mechanism in over here, which gives you the current market estimate of this value. Then you get a new stock features in like some amount of time, you get X2, and now you want to predict Y2. You don't want to predict Y2 just independently of X1. I want to take into account this history. So what I'm doing is I'm computing X1, I'm using X1, X2, and predicting Y2. So X3 like this, and I have a prediction Y3, so on. So what is this? This is a sequence to sequence model. You're using these sequence of inputs to predict the sequence of outputs, right? And why am I calling the outputs a sequence? Because they are basically learned from, there is a causal relationship between, or time relationship between these inputs. X1 occurred before X2, X2 occurred before X3, and Ys should also take into this account. They can use this causality to improve the estimate of the outputs. For example, if I know that over here, when I'm doing the prediction for Y2, if I know what was the output Y1 and what was the input X1, in addition to knowing X2, I can probably improve my estimate of Y2. So these are like called sequence to sequence models. And I want to use neural networks to solve all these interesting problems, predict the future values, predict the next word that is coming out. So what I want to design is a set of neural networks which can help me with these sequence models, sequence predictions. So for that, we will use recurrent neural networks. If I use a simple neural network, the dense neural network or the convolutional neural networks that we have studied so far, one of the main problems is that to predict, for example, Y3 over here, what's the problem? That to predict Y1, I will just need a neural network which is doing this, taking X1 as an input, giving me Y1. But when I come to Y2, my neural network also needs X1 as an input, X2 as an input, Y1 as an input to predict Y2, right? So every time I predict the new value, the inputs of the neural networks change. Their size changes. So I have to redesign this neural network for every stage. I don't want to do that. So we want to build a sequential neural network. Attack this problem in a different way and predict just these outputs. So for that, I will now do it. I will think of it as function, and we will see how to build these recurrent neural networks which fix this problem of changing input size. And so another problem with changing input size is that if you are too far into the future and you need a lot of history, the neural network becomes really big because you have a lot of inputs, all the history is going as inputs, and that means you have a lot of weight parameters, and you have to train all of them to learn the outputs. So that's also infeasible. Probably the time series that you're trying to learn, that is not as complex. This thing, ये जो time का signal मैंने बनाया है, the one in red, this is called time series because it has like this causal element in it. These X, I's are related as they have causal relationships with each other. X tau comes after X tau minus 1. So let's now see how can I set it up. So I will be using these notes in this deep learning book, which is available online. I think you must also be using this book for the deep learning class. So this is the chapter 10 of this deep learning book. This book is available online. So I will be using this to cover this recurrent neural networks and LSTMs. So you can access it online and read this chapter 10. So let's now set this up. So here it is. I will just use the convention which is being used in this chapter. So what is, so let me just write it down. So it is, so here is the, as I just wrote in the previous page, that's the neural network that we have been dealing with before. This is given to us. This is our training data. And now, as I just mentioned, every time I want to compute y, I have to, let's denote it y tau. What I have to do is I have to take in x tau up till x1. When I want to do compute y tau plus 1, I have to take in x tau plus 1, x tau till x1. So this is a function which is neural network. Theta is the parameters. These are the inputs, and this is the output. So you can see that the inputs of these functions are changing every time. So what I want to do is I want to get rid of this. So here is one way to do it. So you take this f, and for the first input x1, it gives you state s1. Or let me just represent it by h1. And then I take this state, and when next input comes, x2, I give it the x2 input, and I just give it the state h1, and I predict the next state h2. And then next time, when I have x3 as input, I don't give it all the x1s and everything else. I just give it h2. h2 is kind of a representation of, or a state of whatever happened before x3. So h2 is kind of holding all of that information in it. So I use this history h2 along with the current value x3 to predict the next state h4. Once I have h4 and I get now x4, I don't want to look at all the x3, x2, x1. I just want to look at h4, use it, and predict the next state h5. So this is a state which is holding all the information about the history. And what is a good thing about this state is now every time this neural network has a fixed size. F theta is your neural network. You can see every time it just takes the current value of the feature vector, x2, x3. Either it takes x2 or it takes x3 or it takes x4. All these x2, x3, x4, they have fixed size. And in addition to that, it doesn't take anything in the history in the form of a sequence which keeps changing, like over here. This sequence was we didn't know how long it would be, so it was just changing all the time. Now we have instead of this history in our sequence, I have this vector h1, h2, h3, sorry, this should be h3, and this will be h4. Okay, so this history vector is just containing all the information about the past. Right, so my neural network is fixed. One thing over here is and someone would ask me what happens to the first time this neural network is used. So over here, I will assume that I'm giving some history h0, which is just an initial vector, which is probably 0. I'll just initialize it with 0, or use some other convenient or relevant initialization that you want to use. All right. So now all of time, the neural f is now fixed. The same neural network which takes the current value plus the history, to predict the next state of the neural network. That's what I'm going to do. So there is kind of a recurrence. You take h0, you predict the next, and then you take it again and you predict next. So there is a recurrence in states. So we'll see how to train such neural network. What is the best way to train it? So next time, let me just show you a recurrent neural network over here.